Hi everybody, my name is Ezra Engel. I'm with the Lab for Nuclear Security and Policy, and today I will be talking about nuclear disarmament verification via resonant phenomenon and some other adventures in nuclear security. We don't have a ton of time, so if there's any follow-up questions, find me afterward. I'll stick around and I'll answer those questions or point you to someone who can. We'll head right into it. So the first session of the 116th Congress dealt primarily with issues of nuclear security. The primary thrust of that meeting was first strike use of nuclear weapons, but also key to that meeting was the state of the global nuclear inventory as of today. So they brought in a panel of experts, as Congress does, and they asked them whether the global nuclear stockpile over the past 20 years has increased or decreased. And we'll get some audience participation here. By show of hands, how many people think that the number of nuclear weapons in the world has increased in the past 20 years? Okay, so those of you who raised your hands, you're in good company. 4 of the 5 experts agreed with you and said that the nuclear weapons had increased in the past 20 years. I have bad news in that you're all wrong. In fact, there's been a dramatic decrease in the number of nuclear weapons globally stockpiled since 1987. And the good question to ask when you see this chart is, what happened in 1987? That would be the Intermediate Range Nuclear Forces Treaty. I have more good news. Arms control agreements work as long as they're implemented well and they're implemented in an enforceable way. And in 1987, we passed the INF, and it led to a massive decrease in nuclear weapons around the world, along with a number of other arms control treaties, both before and after. This is sort of key to the U.S. nuclear posture even today. As of 2018, the U.S. still seeks arms control agreements that are sort of centered around nuclear weapons, but key to that is that they are verifiable and enforceable. Reagan has a great line, just trust but verify. And in sort of arms control agreements, this ends up being very important, that you can verify that the other side is also acquiescing to their terms of the deal. So that's what LNSP does. The mission of LNSP is to provide policymakers with additional technical means for verification, security, and diplomacy. We provide policymakers with the tools so the policymakers can go ahead and make that policy. Well, why is this difficult? So nuclear weapons are an advanced weapon system, and such the design information associated with those weapons is quite sensitive. The verification process has to protect that design information. So how have we gone about that in the past? We have not verified nuclear weapons in the past. We have verified the delivery vehicles associated with the delivery of those nuclear weapons. That's a significantly easier problem because these delivery vehicles are big. You can just disassemble your bombers in the desert, and the other country can fly over and take pictures of your disassembled bombers. Or you can look at the ICBM, which are these big rockets, and just make sure that the rocket is no longer functional. The verification of the actual nuclear weapons themselves is a more difficult problem, and that's the challenge we're trying to address, which is to authenticate the warheads without revealing secret information, because what we've been left with is the surplus of stockpiled nuclear weapons and the stockpile of fissile material, which is nonetheless dangerous even if it's not attached to delivery vehicles. So for those of you who've never seen a picture of what we're dealing with, that's a W-88 MIRV. There are 10 W-88 warheads on that MIRV. Each one's about the size of a 6-year-old child. And that MIRV contains more firepower than all the munitions dropped during World War I and World War II, including Hiroshima and Nagasaki combined. So that's some context like why it's probably a good idea to get rid of these things, but it's also some context, and that thing's really black boxy. Like, is that thing made of plywood? Like, when you see someone destroy that, is that an actual nuclear weapon, or is it some fake? Is it some hoax? Are they destroying a hoax so they can maintain possession of valid nuclear weapons? The important piece in that we try to verify is actually called the PIT. It's the plutonium hollow sphere, which is the central physics package of the weapon. It's the thing that goes boom. It's the thing that makes the bigger one go boom. And from now on in the presentation, we're going to call that the PIT. But when I say PIT, think the hollow plutonium sphere, the center of really most modern nuclear weapons. So how do you verify that the plutonium sphere is in there without learning anything about the plutonium sphere? And we do that with template verification. The idea here is you pull some known nuclear weapon out of a missile silo somewhere. You know that's a real nuclear weapon because if a country is stocking its missile silos with fake nuclear weapons, that country's in a lot of trouble. And then you compare that known copy to interrogated copies. So you pick some A1, A2, A3 from some stockpiled base somewhere. You compare the readings on those warheads with your original known warhead, and if those signatures match, you got a pretty good sense that those things are good matches and that they're valid warheads. And if they don't match, you know the country's trying to pull one over on you. This has a few sort of questions associated with it. Do you use active or passive measurement of that plutonium device? These are radioactive materials, so there is passive radiation associated with the nuclear weapons, but you can also probe it with neutrons or gamma rays. How do you protect information security? The national labs have primarily focused in the past on electronic information barriers, but that's made people kind of queasy because people never like computers, especially when it deals with very, very sensitive information. So we focused on physical cryptography because you can't hack physics. And finally, hoax sensitivity. So any regime you come up with these measurements needs to be both isotopically and geometrically sensitive. We've settled on the use of resonant phenomenon to provide isotopically unique fingerprints for these weapons. And the reason resonant phenomena are nice is because each isotope in the periodic table has a unique cross-section, which sort of the likelihood of interaction associated with it, and that cross-section arises directly from the underlying physics of the nuclear structure. On the left, you see an epithermal resonance transmission cross-section, which is essentially the transmission, like the scattering and absorption probabilities for low-energy neutrons. And on the right, you see a nuclear resonance fluorescence plot. And right now, we are focusing primarily on the resonance, on the epithermal resonance transmission as a means to verify nuclear weapons in an isotopically and geometrically sensitive way. So the way we do this is we take some neutron source. That can be a DT source, which is a little bit what Sean was talking about earlier. Although in this case, the DT source isn't actually producing energy. It's just producing neutrons. Or you can take a LINAC source, which is what we used in the experiment I'm about to describe, which uses an electron accelerator. You push those neutrons through a moderator to slow them down to the relevant energies. You push them through a target. In this case, it's sort of this polyplutonium sphere. And you detect them on a lithium glass detector. Because detectors can't generally parse out the energy of an incident neutron directly, we use time-of-flight reconstruction techniques to actually back out the energy of incident neutrons out the detector, which I will also describe in a moment. And for zero information, and for sort of physical cryptography purposes, we also take these measurements with a piece of encrypting foil. And that encrypting foil is made out of the same material as the target with different isotopic configurations and concentrations, and that masks both the geometric aspects of the target itself, and it also masks the isotopics of that target, providing information and security within certain useful bounds. So making neutrons, you can do it with the DT source, as I mentioned, but you can also do it with a LINAC source. You have a pulse source of electrons, which undergo Bremsstrahlung breaking radiation in some sort of lead source or high-Z material. Then they undergo gamma-N reactions in beryllium-9, producing a bunch of mega-electron-volt electrons, some of which are moderated down to relevant energies and collimated, and pushed through and target an encrypting foil sort of joint target. For our experiments at RPI and the measurements we did at the Rensselaer beam line, we used molybdenum and tungsten proxies for plutonium and uranium because we do not have plutonium and uranium lying around the lab and it's hard to get. And molybdenum and tungsten have relevant resonance regions in the same areas of interest the plutonium and the uranium do. So we used molybdenum as a proxy for plutonium-239, which is it's all fissile, but the weapons grade stuff in weapons, and tungsten for plutonium-240, which is the stuff you don't necessarily want in weapons. For the isotopic hoaxes, we used different concentrations of molybdenum and tungsten, and for the geometric hoaxes, we used cubic configurations of the materials as opposed to the cylinders we used for our warhead proxies. The time of flight reconstruction is fairly simple. You have a time zero that's attributed with your pulse, and then you have a time of detection, which is attributed with when the neutron actually is incident on the detector. So you know the actual time it's spent in the air, and you know the flight path length, so you can back out the velocity, so you can back out the energy, which is an indirect way of getting an energy, but it's the only way we can get it. So finally, we took measurements at Rensselaer Polytech Institute and their Gaertner LINAC beamline facility back in November of last year. And what you're seeing up top is you're seeing the open beam measurement versus the measurement which is for pure tungsten plates in there. Which is sort of just a calibration measurement for us. And you get a very, very good reconstructed attenuation spectrum for tungsten. We were doing this at significantly thicker samples than the facility usually uses, but nonetheless, we got quite good resonance structures. What you see on the bottom is you see attenuation spectra for tungsten, and you see the resonance dips where we expect to see the tungsten resonances based on cross-sectional data. Those are demarcated with black solid lines. When we added molybdenum, we saw molybdenum resonances, and those are denoted by the dashed lines. And you take away the tungsten, you get the molybdenum resonances. So first we measured the template versus the isotopic hoaxes. That's the 90%, 10% configuration versus a 50-50 or 10-90 configuration of the same material. We compared those two. The geometric hoax was deliberately chosen to actually have the same on-axis measurement. So it's a 90-10, 90-10 isotopic configuration, and on this on-axis, on that z-axis, it actually has also the same linear the same linear cross-section. So that on-axis measurement is identical. We expect to be identical. And then you can rotate it to actually use the tomographic aspect of this technique to parse out geometric information that's lost along that z-axis single pixel measurement. So you can compare the rotated configurations and measurements of those two objects to get the geometric information about the objects. This is a picture of the actual assembly. In the blue, you see the pit object, which is that molybdenum tungsten cylinder. And in the red, you see the encrypting foil, which are these sort of series of molybdenum and tungsten plates. The whole thing was placed in the beamline, which is traveling from left to right in the image. So for the isotopic hoaxes, we got very, very good differentiation between the two. We're using chi-squared tests here, and the p-values for both of them were quite good, and the reduced chi-squareds were way above 1, which is what you'd expect for sort of differentiation in spectra just based on chance. It's even more for the 1090 hoax, which is also expected just based on sort of pure physics and cross sections. The geometric hoaxes are not as easy to see by eye. The on-axis measurement, as expected, gave identical measurements, but the rotations sort of reveal differentiation in the actual objects themselves. You can't see these ones by eye, but the chi-squared test was quite obvious and gave us differentiation to about 5 sigma. And finally, we compared sort of a template to a genuine candidate warhead to make sure that our beam was both stable and we could actually, so we were resilient against false positive readings in sort of hoaxing attempts. And for all the different rotations we got a good match on the measurements we took. So in summary, the experimental results that we got matched up pretty well with the expected spectra and the expected comparisons that we had going in. And we confirmed the validity of the approach, and we also confirmed that this type of measurement and this type of technique was valid to be used with sort of thicker samples and also the addition of encrypting foil in these samples for zero knowledge purposes. So this is sort of just one aspect of what LNSP is working on right now, which is this verification with resonant phenomenon. We're also doing stuff with compact neutron source optimization so that we can do these measurements on site, which has relevant strategic advantages, especially for nuclear weapons verification. We do some stuff in nuclear security. One of the professors' lab was actually sort of a key consult in the Iran nuclear deal back in 2014. Currently working on some signals processing for spectra deconvolution, which involves sort of reconstructing this, which is related to the time of flight reconstructions for the energy spectra. There was actually a poster out there on this. We've done work on materials analysis for sort of centrifuge monitoring and the amount of radiation damage those things have suffered, so you can estimate the amount of uranium gone through them. And finally, we have applications for cargo security. So if you have a question about any of these things or anything we talked about in the presentation, please ask. We have a few minutes for questions, and then I'll stick around afterward and answer any other questions that people might have. Thank you.
Thanks a lot, Ezra. Got time for a couple of questions. Yeah.
So the U.S. has withdrawn from the INF, the so successful treaty, and probably will not have a replacement ready when New START expires in 2021. Do you expect the number of nuclear warheads globally to increase in the next 20 years as a result?
To decrease or increase? To increase. So part of what you're seeing in that graph is actually a movement from counter sort of strategic doctrine to counter force doctrine, which sort of targeting cities versus targeting actual armed forces, which happened in the 70s and 80s when we had better precision guided munitions. So the answer is no, we will probably never see a return to the kinds of numbers of nuclear weapons we had in like the late 60s and 70s. But it certainly makes like the global regime of arms control more unstable. And we could see an increase, although I doubt it. I mean, it's just Russia is not the Soviet Union in any scope or sense.
Yeah.
Is there a question about this templating approach? So as you keep these warheads around and keep them in service for their lifetime, the isotopic composition will change. And so how does templating work if your real warhead winds up being 20 years newer than what you're trying to measure against?
So the isotopic composition will change, but bear in mind that the half-lives we're talking about are on the order of thousands of years, tens of thousands of years, hundreds of thousands of years, and we're talking about spans of about 20 years. So the isotopics will change, but not much. And additionally, when we're talking about specific generations of warheads and specific models of warheads, all those warheads were usually built within about 15 years of each other, and then they were stopped being built. So they're all pretty comparable from like a statistics standpoint. There are small variations, but I don't think we're even sensitive to this.
Yeah, Dennis.
There's one isotope that has a short half. Tritium.
Yes.
4.5 years. So do you have any chance of actually knowing about whether or not there's active tritium in this isotope?
So we focused our approach on the primary. For those people who's not familiar with sort of weapons physics, there's primaries and secondaries in most of these devices. The primary is the plutonium sphere, and the secondary is a salt burner, which uses sort of a boosted fusion device to actually increase the yield of the weapon. For a variety of reasons, that we were told that the more expensive and more difficult part of the weapon is actually the primary, so we focused our efforts there. If the primary goes off, it seems like the secondary will go off regardless of whether or not, of like the design specifications of it. And there's no tritium in the primary. I mean, there's some in the core of it, but the plutonium sphere is the thing that's actually very difficult to manufacture, and so that's what we've gone after.
You had a question?
Yeah, so the general design and configurations for these weapons is known. So particularly, I guess, for the for the major players, the U.S., Russia, China, and so on. So can you tell us in of course general classified terms what kind of details are countries trying to hide that would be detectable by a non-encrypted version of this thing?
That is a super good question, and the answer is that you say the design specifications are known. I'm not going to like confirm or deny whether they are known, but I think the idea here is to maintain plausible deniability about the actual specifications and the dimensions of the weapon, because ostensibly those specifications can be used for counterforce design, like pit melts and a number of other sort of design specifications you use to try to beat those pits. If you look on like Wikipedia, there's tons of stuff there, and I think the idea behind a lot of this is to maintain some semblance of security in the pits. But that's an interesting policy question, and I've never been sure why this is such a thorny issue, because you're right, like the basics of how to design a nuclear weapon have been known, and have been known for about 40, 50 years now.
Let me push it just a little bit.
Yeah.
Are we talking about basic parameters like the amount of plutonium in that pit or the diameter of that pit, or you're talking about, or do you think that people are more concerned about electronics or like the package of the explosives? I mean, what is the...
We're talking more about like the dimensions of the pit itself, so like the diameter and that basic, and then we've actually had some pretty pressing questions about like what the design tolerances of those are and what the effects of those design tolerances are on the actual weapons yield itself. But those are obviously that stuff is really classified, and we have not really. We've been so far unsuccessful in getting collaboration with the national labs to actually sort of investigate those questions. Yes, Jason. Oh, someone else.
Just a quick follow-up. Yeah, some people at the labs have also told us that they're worried about their obligations under the Nuclear Non-Proliferation Treaty, not to share weapons design information with non-nuclear weapon states.
Massachusetts. I just wanted to make a very quick comment about earlier question that you had asked where the number of weapons will increase. So the United States and Russia do not have plans to increase the number of their nuclear warheads. However, what is happening is the United States is making its weapons much more precise. And that effectively is almost the same thing as increasing the number of warheads. The lethality of your weapons goes up, it's almost the same thing as having more weapons. And when it comes to the question of like balance of forces, that is a quite big destabilizing factor.
Last question. Yeah, I think the real worry is you get precision guidance, and when you get better guidance, then effectively you can use a smaller weapon, and so that has multiplied up your force by just the guidance, not by the weapons design.
Gotcha. So I'd ask that any more questions we save till after the expo, so let's thank Ezra once again.